problems test 2, that's where you'll find it. And the way this is set up is we're going to actually do 2 here, question 2, which involves the addition of strong acid, because I haven't shown you how to do that yet. And what you're being given here is the initial concentrations of the acid and the weak acid and the weak base that make up the buffer. You're also given the Ka value up here as well. In addition to that, you're told how much of the strong acid is being added. It's going to be 10.0 mils of 0.150 molar HCl. And you're also told here the total volume. But the other piece of information that's important is that the buffer is made up from equal volumes, and this is going to allow us to calculate the initial volumes of those buffer solutions as well. Alright, so this will show you how to do these kinds of problems, and I will go through and show you how to handle the strong acid addition type problems. Alright, so here we go. We've got this much concentration for our weak acid, this much for our weak base. We'll already assume that we've calculated the buffer solution before anything got added, and that's going to be a pH of 4.71. So when we add this strong acid, we're going to expect this pH to go down. It won't go down by much, but it's still going to go down by a little bit because we're adding an acid, and that's what we expect the pH to do. So here's our total volume of solution. It's 310.0 mils. Our first step is to take that 310.0 mils and calculate what the initial volume of our buffer solutions was going to be. Now remember that the way this buffer was made up was we took equal amounts and there's our buffer there, but to this we also added, in this case it was 10.0 mils of HCl. So the total volume here was 310.0 mils. If we take out the 10 mils of HCl, we're left with 300 mils, or 300.0 mils, which means that in order to make that 300.0 mil solution, each of these would have had to have been 150.0 mils. So we would have added those together to get to 300, and then we add in the extra 10.0 mils of HCl, and that brings us up to our given total of 310.0. So that calculation is reflected here. These two volumes are going to be the same. We get it by taking 310.0 minus 10.0. Take that divided by 2, we get 150.0 mils. Our first mission is to find the number of moles of acetic acid in the initial solution, and we do that by taking the concentration and multiplying it by the volume in litres. So it's 150.0 mils converted into litres, which is 0.1500 litres, when we're keeping our significant figures going here as well. We've got 3 sig figs, 4 sig figs. The number of moles here will be 3 sig figs. 3 sig figs, 4 sig figs, 3 sig figs here as well. So everything's kept up. Down here we've got 0.150 moles per litre on the moles of HCl. We had 10 mils, which is converted to litres as 0.0100 litres. This gives 0.00150 moles for our moles of HCl that we're going to add into the solution. So now we've got our initial concentrations. Those are important values. I'll go ahead and circle those. So that's for acetic acid. This is for acetate ion. And this is for HCl. So those are initial moles right there. Alright, so now we've got to figure out what happens when these react. Now the reaction that we'll be interested in will be the A minus plus the H plus gives AH. In the previous example we did, what we noticed was that it was the AH that reacted with the OH minus to give A minus. So here, out of this solution, which you'll remember is going to be a mixture of AH and A minus, the one that's going to react with the H plus is going to be the A minus and not the AH. So just as we had noticed before, this is going to affect both the amount of A minus in the solution and the amount of AH in the solution. Let me illustrate. Alright, so this is the one that we're looking at. Let's say we've got a buffer solution, we've got 4 AHs and 4 A minuses. We're going to add in 1 H plus. Now what's going to happen is the A minus is going to react with 1 H plus to produce AH. And only one of these A minuses that I've got over here is actually going to react with the H plus. So the A minus that reacts with the H plus becomes AH. So now we're going to be left with, instead of 4 AHs in the solution, we'll now have 5, and we'll have 1 less A minus as well. The 1 less A minus is because one of those reacted with the H plus. So we've got two things happening here simultaneously. An AH is getting added and the A minus is going down. Right, just to further illustrate that, let's say in a solution you've got a bunch of A minus and a bunch of AH. And I'm going to add 2 H pluses to that solution. What's going to happen is the A minuses here will react with the H pluses here and turn them into AHs. The net effect of all of this is that the AHs have increased by the amount of H plus that we added. The A minuses have decreased by the amount of H pluses that we added. And that really is the core point of all of this. Alright, let me get rid of that. So, how do we find out the number of moles of acetic acid and moles of acetate ion after the reactions occurred? Well, as I just said, with the moles of acetic acid, we're going to add the number of moles of HCl, because the moles of acetic acid will go up by as many moles of HCl that we added. So we take this value, 0.0225 moles, and add 0.00150 moles. That gives us the new total of acetic acid in the solution. The acetate, the reverse happens. The moles of acetate will go down by the number of moles of HCl added. So I take the 0.0210 moles and I subtract 0.00150 moles. That's the amount of HCl. And that gives me 0.0195 moles. So just repeating that, when acid is added, AH goes up, and it goes up by amount of HCl added. In this case moles, but we can just say that. And the A minus simultaneously goes down. By the amount of HCl added. In the case of the base, it was the reverse situation. You can go back and take a look at that mini lecture to see the same effect as happened here, except in reverse. Alright, so these are our new total moles, 0.0240 moles on the acid, 0.0195 moles on the base. Our next step is to calculate the concentrations of those, and we do that by dividing each of those moles by the total volume in the solution, of course converted to litres. That total volume was given to us in the problem as being 310.0 mils, and we're converting that to litres, 0.3100 litres. Again, keeping our eyes on the significant figures each time. So these are the new concentrations, 0.0774 for the acid, 0.0629 for the base. Alright, now we can handle the rest of this in accordance with the way we were handling the other ones. Alright, so the last step is to state what the concentrations were, and we're making the assumption here there's no H plus in the solution yet. So we've got 0.0774 on the acid, 0.0629 on the base, and we've got H plus as being 0. Now what's going to happen is that the H plus is going to go up by a certain concentration. That concentration I'm calling delta. And it's going to go up because the because the CH3COOH is going to break apart, and it's going to break apart into this and this. So if there were 3 of these, it would break apart into 3 of these and 3 of these. So this would be 3, but this 3 would be in addition to the 0.0629 that was already in the solution. And of course the acetic acid is going to go down by the 3 then. So we're just talking molecules here if we were looking at that. Alright, so this part of it with the minus delta and the plus delta, it doesn't change whether or not we're adding acid or adding base to the initial buffer solution. I want you to remember that. Alright, so going through the rest of the problem, we make the same assumption to weak acid because it's a buffer, and buffers have to be made from weak acids. So we make this assumption that 0.0774 minus delta is going to be 0.0774, 0.0629 plus delta is going to be 0.0629. We substitute those values into the Ka expression, including the Ka which we're given, and calculate delta. Delta is going to be the same concentration of H+. We find the pH, and it comes out to 4.65. You might recall from the initial problem that the pH of the initial buffer solution was 4.71. And that's the original buffer right there. You can see the pH has dropped to 4.65. So we've experienced a drop due to the addition of the strong acid, but it's not a huge drop, it's just 0.06 pH units.